All right, trying to get situated here. Um, Want to continue our discussion from the last class about solving inequalities, so we can focus on them a little bit more in our worksheets. And so I've got just this one board, so I don't have the classroom, but I'd like to put these questions up, these inequalities that we're going to solve. And so hopefully, I'll keep that steady. You can pause the video, copy those down. I'll do them one at a time. I'd like to be able to shift back and forth from in a classroom setting, but not possible at the moment. So they all have something in common in terms of the way in which we're going to solve them. And we've got two typical techniques, one more favorable for calculus study and the other for coming up with some quick answers. So let's do both. I'm not sure if I want to do both at the same. I could probably do both at the same time, and hopefully we start focusing on these a little bit more in our upcoming work. All right. So let's start real basic idea: x minus 5 greater than 0, and then we'll build up to some more challenging problems. So in calculus, we have a topic or not sure it's a topic, but we often refer to certain numbers as being critical. All right, and there's a kind of a strict definition. Maybe it's not so strict, but there's a definition for it at the calculus level. I'd like to extend that concept into our work now at the pre-cal algebra 1, algebra 2 level, that they are important numbers. They're just numbers that jump out at you, and for good reason, for analysis. And obviously, the number that's jumping out at us here right now is the number 5. All right, so let's get a little table, and we'll do just integer work here. So we've got x minus 5 as a calculation. We've dropped something in, and obviously 5 is critical. And it gives us a very nice round number, 0. Well, there's 3 types of numbers. There's 3 categories of numbers. They're negative numbers. I mean, I suppose we could talk about rational. Anyway, some general categories. Negative numbers, 0, and positive numbers. And when you go from a negative number to a positive number, we call that a sign change. Okay? Some people would say it cuts through the x-axis, or say it bounces on the x-axis. We're going to try to refrain from using that language. Numbers don't bounce. Okay? But numbers do change, and the amounts change from one number to the next. Sometimes numbers are positive, sometimes they're negative, sometimes they're 0. A number less than 5. Let's just work with integers. 4. 4 minus 5, negative 1. Number bigger than 5, 6. 6 minus 5, positive 1. That's a sign change from negative to positive. And we can see graphically the linear function, x minus 5 going up at 1 to 1. At 5, what do we get? A sign change. So there's the visual that takes place with that. Okay? You could have, in algebra 1, just moved the 5 and said x is greater than 5. Yeah, that's visually when all these x values here, when put into the equation, kick out positive numbers. That's the general idea that we're going to expand with the more difficult questions. It's the basic idea. All right, so we're going to try to find those important numbers, and then we're just going to check what are called intervals. This is an interval, x less than 5. That's this interval right here. And those kick out negatives. That's x greater than 5 on this side. Now, algebra 1, you might have had an open circle pointing in this direction to represent that interval. We're going to start to use interval notation. So this is negative infinity over here. I just put it there. There's a little more formal stuff here, but we're going to ignore that for the moment. And we go to 5. So from negative infinity to 5 represents that interval. Now, if I colored in the circle, then it would also equal 5. and we change that to a bracket, and that's interval notation. And I'm going to write our answers in kind of shorthand interval notation. I'm just trying to get the concept in front of us so that the rest of the semester, we will be able to tackle these problems a couple of minutes a day for the rest of the year. I'm feeling we're going to get pretty good at it. All right, so let's up the ante a little bit and continue to up it until we get to that last problem. We'll see that we're basically going to do the same thing each and every time. So this is what I wrote. I've got it in front of me there. X minus 4, x plus 3, the product, and I want it to be less than or equal to 0. I hope you can identify the important numbers. I mean, if we want to be less than or equal to 0, I think we better find out when it's equal to 0, and we've certainly done enough work at this stage to say, okay, positive 4, negative 3. What are we going to do? Let's check some numbers, see if they work. Can you think of a number bigger than 4? How about a billion? What if I put a billion in here? I think I'd get a positive outcome. If I put a billion in here, I think I get a positive outcome. Is a positive times a positive less than or equal to 0? I don't think so. False. Well, what happens at the number 4? This is to the first power. We just looked at that problem last minute ago, x minus 5. You get a sign change. So now when I put in a number between negative 3 and 4, how about we put in a 0? Put in a 0, you get negative. Put in a 0, you get, oh, didn't mean to do that. That's the last thing I wanted to do. Is a negative times a positive less than or equal to 0? Absolutely. How about when I put the number 4 in? 4 minus 4 is 0. 0 times 3 equal to 0? Yeah, then that works too. So will this one. Now what happens at negative 3? Well, that's to the first power. Going to get a sign change. If you get a sign change, all right, we put in, probably should go back to the other one just because I want to highlight something. So when I put in a 0, I get a negative. When I put in a 0, I get a positive. Now I'm going to pick something less than negative 3. Minus a billion. Minus a billion minus 4. It didn't change this. This is still negative. But what happens with minus a billion plus 3? You get a sign change. Okay? Minus times a minus is a plus. Is a plus a positive number less than or equal to 0? Absolutely not. Okay? So what we're really talking about is what happens in products or quotients. I mean, I got, you can express division as multiplication. 10 divided by 2 is 10 times a half. And so it's still the same issue. So you have a positive times a negative, which is a negative, times a negative is a positive, times a positive is a positive, times a negative is a negative. It all depends the interval and how it affects the outcome of a calculation. So we also want to do this from the standpoint of graphing. All right, we've done enough work to know what x minus 4 times x plus 3 is. We know it's a quadratic, fancy word for rectangular relationship. All right, length times width. Okay, we know that's not a linear relationship. Let's go to the important numbers again. Positive 4, negative 3. So we know it's a positive a term, right? It's positive, so we know it's a parabola. This doesn't matter. It won't be hard to find. I had the 2 up, so 1/2. But let's just look at what we started out to look at. I'm looking for where it's less than or equal to 0. It's true between negative 3 and 4. Or equal to, excuse me. It's true, I'll put a bracket here, over this interval. That's the interval. Well, from a graphical standpoint, can we see why? Y values, these are Y values, yes? That's a 0. These are all what kind of Y values? Positive. These are all what kind of Y values down here? These are all negative. So these are all negative Y values. Negative Y values. That's certainly less than or equal to 0. Okay? So our final answer in interval notation, you could have done x is less than or equal to 4, greater than or equal to negative 3. That's certainly acceptable. Interval notation, negative 3, comma 4. That's what we'll be writing. Okay, and we'll talk a little bit more formally about that in future explorations. All right, so let's go to the next problem. So you got a choice in all of these things. You got a visual representation with the graph, which I prefer. Over time, you'll move more in that direction, or what's called a sign chart, which is what we've been creating with the true, false, true. All right, so now we got 2x plus 10, and now we'll start to get towards the way I hope you do this, so that when you get to a calculus class and you study derivatives, your teacher won't have to stop and teach you something that's prerequisite for getting into that class. All right, so 2x plus 10. Unfortunately, we too often have to reteach things greater than 0. All right, so reiterating, how do we start? I don't see why we can't say critical numbers, but perhaps that's going against the grain a little bit from a standpoint of its definition in calculus. Let's just talk about important numbers. What are the important numbers? Okay, -5. What do we get at -5 here? What is the graph of 2x plus 10? Let's see, y-intercept 10 up 2 over 1. What happens at -5? Oh yeah, get a sign change. Negative to positive. Oh yeah, that's probably important to keep thinking about. X minus 2 squared. Oh, let's take a look at that from a graphical standpoint. X minus, oh yeah, quadratic. Not drawn very well, but 2, 0 for a vertex. So what happens here? Well, we go from positive to positive to positive to 0 to positive. No sign change. There's no sign change. Geez, I guess if I pick a number less than 2, let's put 0 in there. I get -2 times -2. I square -2. Well, that's actually a positive times a positive. I'm sorry, that's a positive outcome. Okay, I'm jumping ahead. What if I put in a 3? I get 1 times 1. I don't get a sign change. You're going to find out as we do more and more of these that when the exponent is even, you get the same result as if you were just multiplying positives, okay, for that term. All right, so let's do the sign chart, and then we'll come back to how I think we want to learn how to do this in the long run from the graphical standpoint. So we put in a 2. Notice I put a little dot because I want to remember in a little while that I don't get a sign change there. Okay, so let's pick some numbers. I better write the number 2 here. Let's pick some numbers. Let's pick a billion. Nah, let's pick 3. We just pick 3, or a billion, or 4. I don't care. Pi. 2, let's see, 9 7/16. Okay, doesn't matter. Any number bigger than 2 is going to make this a positive times a positive, right? Positive squared, right? And this is certainly positive. So I guess this is true. And we don't want 2 because it say it's not equal, so this is not going to work, number 2. Let's pick something between. Let's put a 0 in. Well, we put a 0 in, we can see we get -20. All right, so we won't be taking any more time with that one. So -20 gets us, wait a minute, I hope I didn't make a mistake with the square. Anyway, we get a positive here, put a 0 in, I'm still waking up, and a positive here when you square a number positive. So we're going to get a positive outcome, which is certainly true. Okay? I did butcher that y-intercept a second ago. That's all right. -5 gets us a 0, so we don't have an equal sign there, so that's not going to work. And this is to the first power, so we said we're going to get a sign change. So let's see what happens when we put in a number less than -5. Let's put -6 in. -6 minus 2, -8 squared, that's still positive. Okay, that's always going to stay that way. But when I put this in here, I get a sign change. And when they have a product, let's just get rid of that, a product, a negative times a positive, we are less than 0, so that is false. So what do we have in interval notation? This is where interval notation gets to be a little easier than the other types of notation. we go from -5, which does not work, to 2, what does not work, but also we get 2 to infinity. And that's matching up with what you're seeing up here. Okay? All right. So now we'll continue on a little more. Oh, the graphical standpoint. Excuse me, that's what I really wanted to get to. So let me clean this up a little bit and show you how to do this from a graphical standpoint in the way that I think is the easiest. All right, and the way to do that is to, again, just find the critical numbers or the important numbers. 2, oh, sorry, I wanted to, that was squared, I believe, right? So therefore I'm changing that because the way I originally wrote it is to the first power, and I get a sign change at 2 in a linear function, but in the quadratic, I don't. And my way of remembering that is put a little dot there. All right, and -5, you will probably have heard more language like cuts through the x-axis and bounces, but I already told you what I think about that. So I'll argue that point, and not against any personalities or anything, but my own preference is that language matters and numbers don't bounce. Okay. Oh, sorry, gotta wake up here. Where was it? Oh, the graphical. All right, so let me get rid of this, and let's just say this is the problem that I see in front of me, and how would I do it? Because I always believe the quickest and easiest way is the way you should eventually do a problem, but we want to recognize if you have different ways of doing things that are valid, yay. All right, so I look at this and I go, okay, the biggest number is 2, so I'll pick a number bigger than 2, and I know I don't have a sign change there. So I'll pick 10. 10 minus 2, 8, 8 squared is positive. So therefore, this thing is going to positive infinity. And I will graph backwards now. No sign change, sign change. There we go. So there's the graph, the general shape of this curve. And I asked myself, when am I greater than 0? Certainly this interval here and this interval. And that's why we had -5 to 2 union 2 to 5. 2 to infinity, excuse me. All right, so it's quick to do one. I'll just make one up real quick, and then I'll get back to the ones that you were written down, just to show you kind of without talking. I'll try to add a little accuracy to the curve. Prior to that, I will probably say that these are sometimes we call it those parentheses linear factor, quadratic factor, cubic factor, so on and so forth. And they take on the look. They take on the look. There's a cubic. All right, so they take on the look of the particular type of calculation that to the power that you're looking at. All right, so let me just make something up real quick. Let's do 2x minus 3. We'll do squared times x minus 4 times x plus 7 cubed, and let's just get greater than 0. So I look at this and I find the important numbers. We got 3 halves. It's to the 2, so it's going to have a dot. 4 linear function, 4 -7 cubic function, and that's to the first power, so that's why I put that there, -7. So now I pick a number bigger than 4, 100, positive, positive, positive. Okay, so I know I'm moving in the positive direction. It's a cubic, so it's going to have a little bit of a cubic look, right? And there's your graph. When am I bigger than 0? Negative infinity to -7, 4 to infinity. Okay, and you know, I make mistakes sometimes talking and doing, more so now as I get older. So I do believe that's correct, and we'll do some more problems. We'll give you a crack at one now. Now that we've done enough of these, why don't you sit back and this is a little out of order. Now let's do the absolute value right now, and then we'll come back to that. I think it'll be better for you. So the one that I put down was 3x minus 8 plus 5 less than or equal to 17. Okay. So what have we been looking for? Intervals. How do we find those intervals? We look for the important numbers. What are the important numbers here? Take a moment. Now you might have said 8. 8's important graphically. Sure, it's important graphically, but it doesn't generate answers for this particular problem. Actually, there's a shortcut here and it helps a lot, but we'll get to that later. So what are we looking for? We're looking for the numbers that make this thing equal 17. Okay, so first off, absolute value very quickly, right? If you take the absolute value of x, what happens when you take the absolute value? All the negatives become what? Positive, and you get that V-shaped graph. Okay, so we know we got a V-shaped graph here. And you get a sign change here, and then it negates the absolute value, negates the sign change. All right. All right, so the way I solve absolute values is I break it up into its pieces. It takes a little bit longer to write, but it's mindlessly easy. So I do it. So x minus 8. And we have studied how to write these in, I think I get the negative and the positive, yeah. All right, so subtract 5, 12, divide by negative 3, negative 4, add 8, positive 4. Okay, so that's one of our important numbers, positive 4. Subtract 5, 12, instead of getting negative 4, you're going to get positive 4. And then what did I do? I added 8, so 12. So let's just check that real quick. 12 minus, let's put it in the original. 12 minus 8 is 4. 4 times 3, 12, plus 5, 17. And let's add the two numbers, 4 and 12. Just some helpful things to think about. 4 and 12 is 16 divided by 2 is 8. Okay, so there's symmetry here between those two points of intersection. So this is good, 4 and 12. All right, so now what are we going to do? The same thing we've been doing all along. Plug it in, see if it works or not. Number bigger than 12, a billion. Less than or equal to 17? Absolutely not. False. These things change signs, by the way. So you could have just done that. But you take the time, put some numbers in, see that those intervals work. And it's also equal here. You got to remember it's also equal. So when am I less than? 4 to 12. So I might be nicer to write it this way. Okay, so it's not confused with a coordinate. Although 4 to 12 here, inclusive, like so. Okay, now let's look at what's going on from a visual standpoint. Well, would have been, well, all right, let's just look at V-shaped graph, 8, 5, the vertex, right? And in class, I've been asking you to find the y-intercept, just put it someplace here. And we know 17 is going to be up here, yes? All right, so let's find the y-intercept, 24 plus 5, oops, geez, I should have. The old guy's making mistakes here. So this is 24 plus 5, 29. That's helpful now. Why is that helpful? Because we can see 17 is less than that. So I don't know why I made that mistake, but I did. All right, so we're looking at y equals 17, and we got points of intersection here. Hopefully you can recognize what those x values are. Yeah, they're 4 and 12. 4 and 12. And we want it to be less than 17. Well, 29 is not less than 17. 30 is not less than 17. 40s. These numbers are not true. Remember? What is true between 4 and 12? Inclusive. Okay, so there's the graphical. But we're still doing the same thing, identifying important numbers and then just looking at intervals. All right. All right, so now we got away from the polynomial for a moment. Let's go right back to it. And if you should be pausing the video each time I put one of these things up, and you should be trying it before I give you the explanation, or hopefully the correct solution, although I'm kind of having a fatigue day here. I'm trying to get this thing done in a hurry because we're going off on a trip in about 20 minutes. So, all right, your try. All right, you did, you tried, we're back. I'm going to do it from, we'll do it from the sign chart. So 4, let's see, 4 is the biggest number. So 4 dot, well, hopefully we remember why, -6 and 0. Doesn't have to be drawn to scale here. I just try numbers, a number bigger than 4, positive, positive, negative. This is negative. If I put in a number bigger than 4, like 100, minus 2 times 100 is a negative number. 100 plus 6 is a positive number. 100 minus 4 squared. This is always going to be positive. No sign change, hence that's why that's a dot. All right, so where the heck am I? Greater than 0. Okay, and we said it wasn't. So if that's false, no sign change, that's going to be false. Sign change, that's going to be true. Sign change, that's going to be false. So when is this thing greater than 0? -6 to 0. So probably, but not equal. I didn't say equal. Haste makes waste. You can see I'm going a little too fast, making some careless errors, but I got a nice eraser, so no big deal. All right, so now let's do it from the graphical standpoint, which is how you would analyze this. Would need to analyze this in a calculus class, because there's more information coming from these graphs than we're talking about right now, and we'll expand on that when we get mechanically good with this. We'll have that conversation. I can't have it right now because I'm in a hurry. All right, so maybe I will have it. What was I planning on doing? Oh, yes, from a graphical standpoint. So I'm just going to be quiet. I'm just going to do it. Bigger than 4. I said I'd be quiet, but I think I better talk. Bigger than 4. This is positive. Bigger than 4. This is positive. Bigger than 4. This is negative. So I hope I didn't graph this before. Okay, so that's a quadratic factor. These are both linear to the first power, so nice change of signs. So that's what that graph looks like. And I think I was looking for greater than 0, and it's between -6 and 0, which it matches up with our sign chart. So if this was a if this was a derivative in calculus, it would represent rates of change. And when a rate of change is increasing, you're accelerating. So you get into some discussions from the graphical standpoint. That's where you're headed. All right, a brief comment on that. All right, so on Tuesday, I'm going to give you one of each of these things along with some quick trig, and that'll be our class on Tuesday. All right, so how do you do 5x minus 10 over x plus 3 less than or equal to 0? That's the one I asked you to consider. If you tried these before doing this, watching this video. So critical numbers. And I think I'm going to change this up a little bit. Okay, I'm going to change this up a little bit in just a second, and then we'll come back to this. All right, so what's critical number here? 2. Why did I put a dash? Because it's a linear factor to the first power. I won't put, yeah, I got an eraser here, right? My finger. Yeah, smudges. Oh, well, -3, right? Now, sign chart. Why not? Just plug some numbers in. We know we're going to get sign changes, so you pick something bigger than 2, 100. 500 over 100. Oh, that's positive. Is that less than or equal to 0? Heck no. False. This is true. This is false. This is true. This is sign change. Excuse me. I went to that one first. So sign change. This is true. This is then false. Okay, so what works? -3 to 2. Okay, I gotta get going here. Oh, what happened if I made this a square? If I made it a square, well, then I don't get a sign change at 2. If I don't get a sign change at 2, then that would have been false as well, and that would have been true. I haven't had my coffee. So check it out. If I'm wrong, email me. All right, but this was the original. Now, these are rational functions. They are, difficult for students to learn how to graph. That's just what I see over the past 40 years. All right, so let's just graph this real quick so that we can see the same answer. All right, first thing you should do is take the y-intercept, -10/3. So let's label this -10/3. Next thing is to look at as it goes to plus and minus infinity, as in, if I go to infinity, this is going up 5 times as fast as that. So we've got an asymptote of y equals 5. We'll expand on that later. All right, so that's, I would not solve this from a graphical standpoint. If I was looking for a quick answer, I would have done the previous method. All right, where are we? Oh, yes, x-intercept at 2 and undefined at -3. Okay, and so we can see that this is doing this, and this is doing this, and this is another topic which we'll try to spend more time on. But where am I less than or equal to 0? Well, certainly not here. These are all positive y values. These are certainly all positive y values. It's the interval -3 to 2. And I believe that's what we looked at before, but I can't remember. I didn't have my coffee. But that's the method we're going to use. It's still division, division. You got a positive and you got a negative. When you divide, you're less than 0. If you get a sign change here, you're greater than 0. That's the same process and discussion we've been having throughout this video. All right, last one. Last one. So how do you handle x plus 6 over x minus 5 greater than or equal to 2? Well, one of the most important concepts or abilities that you want to cultivate is when you look at something and you don't know what you're looking at, can you rewrite it in a way that you do? Okay? What was everything else based on before? Mostly products or quotients equal to 0. Can I move the 2? Certainly can move the 2. Can I do a quick bingo, bango, bongo? How about I put a 1 there for you? Right? Bingo, x minus 6. Bango, 2 times x minus 5, 2x minus 10. Remember, I already took care of that, right? So all you have to do is that times that. So what do you got now? You got a new problem. This is the same thing as x minus 2x minus x. Minus 6 minus a minus 10 is plus 4. And you're over x minus 5. And now you're looking at greater than or equal to 0. Well, there's only 2 critical numbers here, right? Positive 4 with a sign change. Positive 5 with a sign change. Okay, so. And then you plug your numbers in, find out if things work or not. Okay, I got to keep an eye on time here, or I'm going to miss my ride. So that was just to get us started. Obviously, we'll have more lengthy discussions as we go on the rest of the year. There's no rush here. Right? Take your time. We'll figure out how to do this and let it become part of your toolkit. Okay, so the worksheets now, you should be looking for these inequalities. If you're not sure how to do it, ask one of your classmates and just keep doing them until you can do it yourself. Remember, follow. You followed, hopefully. A little haphazard here today. Do it yourself and then hopefully explain it to somebody else. Okay, I hope I didn't exceed my recording times. That would be nasty, and then I'd have to get rid of this thing. Everybody have a good day. I'll see you on Tuesday. Bye-bye.